All right. So for this third lecture, we're going to be talking about optimality. So lecture 3, optimality. So recall from last lecture the two convergence rates that we derived. So last time, we had two convergence rates. One was of the form R0L over square root t. Okay, so this was if I just run gradient descent on a Lipschitz function, so the norm of the gradient is bounded by L, and I start at distance R0 from the optimum, and I do t steps. Okay, so this was just basic gradient descent, maybe projected gradient descent if I have a constraint. And the other rate that I had was R0B over square root t. So this was gradient descent with random gradients, where the random gradients were bounded, the norm squared was bounded in expectation. Okay, so remember the parameters are R0 is your distance to opt at the start. L was the norm of the gradient, so the supremum, say, over x in k of the norm of grad f of x. And B was such that it was an upper bound on the expectation of the norm of gt squared. Okay, where gt was such that the expectation of gt given xt, the point that we carry at time t, is equal to the gradient. Okay, so you remember this if you just do gradient descent with random gradients instead of actual gradients, everything was fine provided that you get an upper bound on this variance term. Okay, so I will refer to this as a random oracle. And when you can actually compute the gradient, this is a gradient oracle. Okay, when we talk about lower bounds, we like to talk about oracles. Just some terminology. So what I'm going to do for the next, I don't know, half hour or something like that, I'm going to prove to you that those rates are optimal. That, this is the end, you cannot do better than that. And then I will talk about why this is not the end. Sounds good? All right, so let me just, since we're going to talk about lower bounds, let me give you a very, very basic reminder of the Minimax principle. So basic Minimax principle, which is trivial, but it's worth noticing it. So basic Minimax principle. So we want to what do we want to show? We want to show that for any algorithm, the algorithm could be randomized. Maybe it's making some random queries, so possibly randomized. We don't want to exclude the use of randomization. Also note that so far we didn't use randomization. Our algorithms are deterministic. The only possible randomness is in this oracle, which we do not control. Okay, so that's different. So for any algorithm, possibly randomized, we want to show that there exists a function and an oracle. Okay, so the oracle could be a random oracle, such that the error rate of gradient descent is optimal. Okay, meaning, what do I mean? I mean that after t queries of this algorithm on this function with that oracle, I cannot get an error smaller than this. Okay, so this is the statement we're going to be after. For any algorithm, there exists a bad function and a bad oracle, which verify our assumption, such that after t queries, you cannot do better than those things. Now, what I want to do now is to swap this for all and exist. Okay, so what I'm going to say is that it is, in fact, it is sufficient to find a random function such that any deterministic algorithm on this function has error rate bigger than whatever. Whatever is the numerator over square root t in expectation. Okay, so instead of fixing an algorithm and then thinking about trying to find a function, I reduce my problem to just finding a very difficult random function. So this is a function, you know the distribution of this function, but you don't know what function I'm going to sample from this distribution exactly. So you can think, I know the distribution, I'm thinking about this distribution, I can come up with an algorithm that depends on this distribution, but then if I run my deterministic algorithm on a sample from this random function, I cannot get better in expectation than this error rate. And the fact that this is sufficient for this one is the basic, the trivial side of the Minimax principle. So this is a consequence of the following fact. This is implied by the fact that min max is always bigger than max min. Okay, I don't want to get more into this than what I said so far. Okay, so this is trivial. If you have a function of two variables, and you're taking the minimum over one and then the maximum over the other one, this is always bigger than if you first take the maximum and then the minimum. You can just think about it as a two-player game. This version is like the minimizing player goes first and then the maximizing player. Okay? So of course, if the maximizing player sees what the minimizing player is doing, it can always do better. It can get a larger function value than if the maximizer player has to go first. Okay, and the Minimax theorem is that there is actually equality. But here what I want to emphasize is that this is not a deep statement. This is a trivial statement. It's just you need to wrap your head around it. But there is nothing to be proven. It's true. Okay, so I will let you think about this. Maybe if it's the first time, take some time to get used to it. But I don't want to spend more time on it. Yeah?
So this so-called lower bound is indeed the lower bound for the uniform upper bound. But if you're given a specific function, the convergence rate can still be better than 1 over square root of t, right?
Of course, but you're spoiling the rest of the punchline that I'm going to show this uniform lower bound. And then, of course, it's not the end because these are uniform lower bounds. So if you make more assumptions, you can beat them. Yes, exactly.
What is it that allows us to go from randomized algorithms to only constrained deterministic algorithms?
Right. That's not totally obvious. This fact is convexity. Yeah, maybe I explain to you after. It's just the fact that here, when I take the minimum, so I apply this minimax, okay? So think about it here. The minimization is over algorithm. Maximization is over function. I managed to swap, so now I maximize over random function, and I minimize over maybe randomized algorithm. But the point is, by convexity, the minimum over a randomized algorithm is going to be achieved at a deterministic algorithm. Yeah, that's... Basically, what's the point of randomization from a game theoretic point of view? The point of randomization is so that the other player doesn't know what you're going to do. But here there is an order. Okay, so the max player goes first and then the min player. So if I go second, I have no point in randomizing. Okay, good. All right, so let's do the first lower bound, which is going to be with random oracle. So random oracle lower bound. And you will see my random function is going to be so simple, really, really elementary. So the setting is like this. K is my constraint set is just the unit interval, minus 1, 1. Okay, very nice, very simple. My function f of x is going to be a random function. It's going to be it's going to be psi x for psi, which is equal to either plus epsilon with probability half or minus epsilon with probability half. Okay, so my random function, I just draw it once and for all. It's either a linear function with slope epsilon or it's a linear function with slope minus epsilon. And I'm telling you, this is what you're going to see. You have to optimize this function. Okay, so if the world turns out to be a plus, then the optimum is going to be at minus 1. If the world turns out to be a minus, then the optimum is at plus 1. Okay? That's all I need to do. Note that the gradient of this, f prime of x, is just psi. Right? So my gradients, they don't depend on the point. It's just this psi. That's all it is. Now we are in the random oracle model, so I also have to specify a random oracle. That means something that gives me in expectation psi. Okay, so the random oracle is like this. GT is going to be sampled from a Gaussian centered at psi and of variance 1. Okay, so whenever I call my oracle to get a gradient, I don't get the slope, plus epsilon or minus epsilon, but I get the slope plus some noise. Okay, if you want, you can also think that GT is equal to psi plus ZT, with Z1 up to ZT, IID normal Gaussian. Okay, so the point is just when I query my oracle, I get a gradient plus a Gaussian noise. It doesn't get simpler than that. This is a linear function in dimension 1 with Gaussian noise. Okay, so informally what's happening? So intuitively. What's happening intuitively? So after T queries, what do I want to do? I want to optimize this function, so I need to estimate, is it a plus or a minus? Okay, so I need to estimate the mean of those Gaussian. So the best estimator for the mean of a Gaussian is to just take the sample average. Okay, so after T queries, the best estimator for psi is the sample average. Is 1 over T, the sum for T equals 1 to capital T of GT. But we know exactly the distribution of this thing, right? I mean, Gaussians are closed under addition and multiplication, so what do I get? This is distributed as a Gaussian with mean psi, and the point is that the variance gets reduced by 1 over T. Okay? So this is, if you want, you can view it as psi plus 1 over square root T times Z, where Z is an N01. Okay, so after T queries, I can estimate the slope up to an error which is like 1 over square root T times a Gaussian. So you see, if the slope is either epsilon or minus epsilon, and epsilon is smaller than 1 over square root T, then there is a constant probability that I'm wrong in estimating the slope. Okay, so if epsilon is smaller than 1 over square root T, there is a constant probability to wrongly estimate the sign of psi. Right? Because the deviation of this are of order of a constant. You know, say psi is plus epsilon. There is some probability, you know, I don't know, 0.1 that z is smaller than minus 0.1. And maybe minus 0.1 times 1 over square root T, it overcomes the plus epsilon. So what I get is that this thing, this estimator is negative. If this estimator is negative, I will say, oh, I think I have a negative slope. So let me optimize, with +1. But I'm wrong because it was plus epsilon. Okay, so this shows that you cannot hope to attain an accuracy smaller than 1 over square root t. This shows that this rate is optimal. Okay, so if you want, I can just do a formal lemma, but is there a question on the intuition? No? Yeah?
Yeah, so it's supposed to work for any deterministic algorithm, right?
Yes.
This specific example.
Yes.
Even the deterministic algorithm just samples the function at 1 and at -1 and then chooses the minimum of these two.
No, yeah, sure. I mean, I only get gradients, right?
I know, but my deterministic algorithm can be sample, let x be 1, let x be -1, and then stop there, right?
Yes, but recall we are in the random oracle model. So I don't get the function value. I get it only with noise.
Okay, I see.
Right? So you cannot take the best of, +1 and -1, you will sample those two things, you will get some random numbers. Like more than, 0.4 of the time you will be wrong if you take.
The idea is that you never get to see the actual function value, only the gradients or the noise?
You can also see, if you want, you can also see the function value as long as it's with noise. If you see it exactly, then of course it's trivial. Yeah. The whole point is that the signal is small and it's drawn under the noise. That's the whole point. If you could observe the real function, then yeah, it's very trivial. Yeah.
I'm not following the logic on the epsilon. When are we choosing the epsilon? Because if we're fixing the epsilon first when we define C, then there is some T
Yes.
for which that is not true.
Correct, correct. So here the way I'm thinking about it is that I'm going to fix my time horizon and fix the function as the parameter of the function can depend on the time horizon. Yeah. Yes. But you're right, eventually I will solve this problem.
So we're saying that for any time horizon there exists
Yes.
a function such
That's
that
right.
no algorithm works.
Exactly. Basically what I'm doing is all those parameters, R0, L, and T, I fix them, like this is fixed for the rest of the lecture. And everything is with those parameters fixed. But good question, yeah. Okay, so maybe I just do very quickly the formal statement just because it makes appear nice objects, but this is a proof. So formally, you can write the following lemma. So lemma. So for any function psi which goes from RT to -1, 1. Okay, so psi, it's my deterministic algorithm. It's making T queries. It doesn't matter where those queries are because it's a linear function. So after those T queries, I just observe those T vectors, and given those T vectors, I have to output a point in -1, 1. Okay, so for any such psi, the probability, where the probability is understood both with respect to at the beginning sampling either a plus epsilon or a minus epsilon and sampling all the observations from this Gaussian. So the probability is that the sign of psi on G1 up to GT. Okay, so after observing all these gradients, I output a point in between -1 and 1. I can look at its sign. The probability is that the sign is actually the correct sign. It's equal to the sign of psi. This is upper bounded by 1/2 plus square root T epsilon squared. Okay, so this is a true bound. This is now completely formal. So what is this saying? It's saying that if epsilon is very small, smaller than, say, 1/4t, maybe 1/4t is not great, 1/8t or something, then the probability that I'm correct is upper bounded by 3/4. Or put it another way, there is a 1/4 probability that I'm wrong. And if I guess the sign wrong, I pay epsilon. right? Because if I guess the sign wrong, then certainly my value is non-negative, but the best I could do is minus epsilon. Maybe I write it here. F star, which is the minimum of f of x over x in k. In this example, it's equal to minus epsilon. Okay? And what I just said is that if you're wrong in the sign, then certainly the value that you get is non-negative. So your gap to optimality is epsilon. Okay, so how do you prove such a statement? You prove it like this. So the probability, say when xi is equal to a plus 1, that, let's call this variable xt. Okay, so the probability is that xt is equal to plus 1, plus the probability when xi is minus 1, that xt is equal to minus 1. Okay, so this is what I care about. I care about the average 1/2 times this plus 1/2 times that. So what is this? This is equal to 1 minus the probability when xi is a plus 1 that xt is equal to minus 1, plus the probability when xi is minus 1 that xt is equal to minus 1. Okay, so I'm just looking at the difference. So I'm looking at this event, the event that my xt is a minus 1, and I'm looking at just the difference of probability between this event when xi is a minus 1 and when xi is a plus 1. This, by definition of the total variation distance, is upper bounded by the total variation distance between the probability of xi is minus 1 and the probability of xi is plus 1. So this is upper bounded by 1 plus the total variation distance between this measure, the probability when xi is a plus 1, and the probability when xi is a minus 1. Okay, and what I mean by that, what is still random in there? What's random is the sequence of observation. Okay, so this is a Gaussian with mean minus epsilon and variance 1, but product t times. And this is a Gaussian with mean epsilon and variance 1 and product t times, right? This is a tensor product of my probability distributions. So I have the the total variation distance between these two t tuples. So what I can do at this point, either you know exactly the formula for this, or you can use what's called Pinsker's inequality, which relates the total variation distance to the square root of the relative entropy. So this is upper bounded by 1 plus the square root of the relative entropy between those two things. And then you have the chain rule, and then at the level of one independent Gaussian, the relative entropy between an n epsilon 1 and an n minus epsilon 1 is exactly epsilon squared. So using both the chain rule and the calculation for one Gaussian, you get that this is equal to 1 plus square root, maybe there is a 2, is there a 2, there is a 2, so t epsilon squared with a 2. Okay, so if you didn't follow this, no big deal. It's just to give you some pointers of the literature to look at. So total variation distance, relative entropy, Pinsker inequality, Pinsker's inequality. So these are very useful tools when you want to prove lower bounds. But this is just to prove the formal lower bound. Like the intuition should be very clear just from doing this little argument. Okay, so that's like the end of the formal proof. So that shows that we cannot improve the 1 over square root t rate with a random oracle under those assumptions. Yes?
What is it? It says 1/2 here, and then here it says 1 plus 2.
Yeah, because I missed a 1/2 at the beginning.
Okay.
So, you know.
Yeah, 1/2 plus 1/2.
Yeah, 1/2 plus 1, exactly. I mean, it would be bad if there was no 1/2 here. So, yeah, better has to be 1. Okay, cool. So that's for by the way, this is related to what Kevin was talking about. I think he didn't prove it, but this is exactly the same argument to prove the bandit lower bound of square root t. Right? It's exactly the same thing. I hope he didn't do the proof. Okay, so now let's go back to the deterministic model. Because at the end of the day, you know, okay, in machine learning, it's very interesting to do the random oracle model because you care about the generalization error. But at the end, you can say, okay, I have this function, this deterministic function, it's there. I can compute the gradient. There is no noise. What's up? I mean, if in that case, can I improve? So let's do the deterministic oracle model. So here we're going to look at a very, very beautiful function. So again, I need to construct a random function. Now my random function this time is going to be more complicated. So let v1 up to v, let's say t plus 1. So I have t plus 1 vectors in Rn. Be a random orthonormal set. Orthonormal set. Okay, so these are just like they are mutually orthogonal and they have norm 1. Okay, so I have t plus 1 random vectors like this. If you want right now, you can just think v1 is the first vector of the canonical basis, v2 is the second vector of the canonical basis, and so on and so forth. And then you just apply a random rotation. And if you don't want to think about the random rotations, that's fine. You don't have to think about it. Okay, so I have this random orthonormal set. And I'm going to define f of x like this. Let f of x be the maximum over I in 1 through t plus 1 of the inner product vi dot x. Okay, so I have these linear functions, and I'm just taking the maximum of all of those linear functions. Okay, so this is convex, just because I'm taking the maximum of those convex functions. And K is just going to be the unit ball. So it's a set of x in Rn, such that the Euclidean norm of x is 1. Okay, so let's call this function, let's give it a name, let's call it the Nemirovsky function. It's a very beautiful one, I think. Okay, so what happens with the Nemirovsky function? So when I make a gradient query, what do I get? So we didn't really talk about subgradients and things like that just because it's not that important. But you see, when I make a call to this function, one of the vi is the one currently realizing the argmax. You know, except for a very small a set of measure 0, there is only one vi that realizes the argmax. So locally, this is a linear function whose gradient is exactly the vi realizing the argmax. Okay, so the gradient of f of x, this is vi for I, which is the argmax over j in 1 through t plus 1 of vj dot x. Okay, except for a set of measure 0. Except for a set of measure 0. Of course, this set of measure 0 includes the point 0, so you know you can actually hit it, but it doesn't matter. You can talk about subgradients in general, but I don't want to get into this. Okay, so when you query the gradient, you get one of these linear functions. So after t queries, there is still one of those linear functions that you don't know. After t queries, one of the vi's remain unknown. Okay? By unknown, what do I mean is we know that this last vi that remains, we know that it's orthogonal to everything else. But apart from that, it's a random point on the orthogonal sphere. Okay? So say say it's Vt plus 1. Just we rename things so that it's Vt plus 1. Okay, so after T queries, we have discovered V1 up to V capital T. But there is this last guy, which is random. So what does that imply? So for any x and V1 up to Vt, what do we have? We have that the expectation over f, over the random function f of x, given V1 up to Vt. So let's say I fix this, and I only take the expectation with respect to the randomness of Vt plus 1. This is certainly larger because it's the maximum than the expectation over f of Vt plus 1 dot x, given V1 up to Vt. But this expectation is 0. So what does that tell me? That tells me that for my deterministic algorithm, after making T queries to this random function, the value that I get has to be in expectation non-negative on the Nemirovsky function. It has to be. There's just no way around it. But on the other hand, what is the optimum? Let me do the optimum calculation here. F star, which is the minimum of f of x over x in B, I claim that this is smaller than minus 1 over square root t plus 1. Thanks to the following point, thanks to x, which is minus 1 over square root t plus 1, the sum for t equals 1 to t plus 1 of the Vt. Right? If I just so this is a point in the L2 ball, right? If I just expand the Euclidean norm squared of this thing, then I get the sum of the Euclidean norms squared of those guys, which is 1, rescaled by 1 over t plus 1. Okay, so the norm of x is 1. Okay, this is a point on the sphere. Just like if I'm in dimension d, if I look at the point 1 over square root d, 1 over square root d, etc., 1 over square root d, this is on the sphere. Okay, the same thing. Here I write a point in the sphere of dimension t plus 1, just using this combination of the VTs. Now, if I have this point, then you see that every inner product is minus 1 over square root t plus 1. So the max is minus 1 over square root t plus 1. So the optimal value of this function is minus 1 over square root t plus 1. But if I make t queries, I'm stuck at 0, which is, by the way, what I could get just by querying the point 0, right, just to be clear. So I didn't make any progress at all. I'm completely stuck on this Nemirovsky function. And then once I have, the last one, then suddenly everything clears, and I have this valley, and I can go to this point. But the point is, my gap is 1 over square root t. Okay, so this shows that in the deterministic oracle model, you cannot also get better than 1 over square root t. Is there a question on this proof? Yeah.
The reason why it's 0 in the boundary is because the constraint set is symmetric?
Yeah. I mean, not the constraint set is symmetric. It's more like Vt plus 1 is symmetric. So, if I have, right now I have, this is the current subspace that I have discovered, and Vt plus 1, it could be either that, or it could be the one below, So that's this symmetry which is taken here to give me 0. Yeah?
I guess you didn't mention this, but it seems like t plus 1 needs to be less than n.
Yes. That was going to be my gotcha. Yes. Right. Okay, let me come back to it in a minute.
K is the unit ball, right, not a sphere.
Say again?
K.
Yeah. Thank you. Yes, it should be a convex set, so it's not the sphere, it's a ball. Yeah, very important. Okay. Yeah.
So it seems like you might actually need more than t queries to reach all of them, right? Because you might have queried the same thing multiple times.
Yes, this is a lower bound. So,
Can it be improved though?
No, it cannot, because we know an algorithm which goes at rate 1 over square root t.
Right. So you actually are kind of querying a different one each.
That's right, yes. Basically, you think about it. What is gradient descent going to do? It sees the first one, then it moves a little bit in the negative direction of this. So this little guy is not going to be the argmax the next time around. So every time I get a new argmax. Yeah. Yeah, it's useful to think about what gradient descent is doing on those examples. It's insightful. Was there another question? Yeah, so what's the big gotcha, and why did I do 2 lower bounds? It's because this lower bound is only valid when t plus 1 is bigger than n, right? To get an orthonormal set, I certainly need that the number of vectors is smaller than the dimension. Okay, so this is like important for t, so t less than n. Okay, so while gradient, and this is something we haven't emphasized at all so far, but which is crucial, is that those bounds, 1 over square root t over there, they are dimension free. They don't make the dimension appear. So this is extremely appealing from a machine learning perspective where you want to work with models with millions of parameters. The number of steps is not going to depend on this, on this million of parameters. It's going to be a number that is independent of the dimension of your model. Of course, there is no magic, like each gradient itself, is giving you an amount of information, which is the number of dimension, right? But the number of steps is not depending on the dimension. So what we saw here is that the 1 over square root t is optimal with random noise, even in low dimension. It has nothing to do with high dimension. But with a deterministic oracle, the 1 over square root t is really a high dimensional phenomenon. Okay? So it begs the question, can you improve if your number of steps is bigger than the dimension? Okay, maybe you can do better than gradient descent in that regime. Okay, and yes, you can. So I will just give you one algorithm that does that. And you can think about it like in dimension 1. Okay, maybe think about it while I erase because it's very painful to erase. What would be an algorithm in dimension 1 to optimize a convex function that does better than gradient descent? Is there a proposal? You can just shout answers.
Go as far as you can in the direction of the gradient.
Sure. Yes. That's one thing you can do. Yeah. It's pretty good. The word I was looking for was binary search, but it's more general. But yes, what you said is correct. I mean, yeah. So yes, so you can do much better in low dimension, and we're going to see a general algorithm to do this, which is extremely beautiful and much more geometric. Okay. So. Low dimension. Okay, so I'm just going to tell you the algorithm. So the algorithm is based on the following inequality. So Grunbaum's inequality. From the 50s, it goes like this. For any, so let K be a convex body. For any half space H that contains the center of gravity of K. The center of gravity of K. So what is the center of gravity of K? So CG of K is just the mean of a random point in K. Okay? So it's just 1 over the volume of K of the integral over k of x dx. Okay?
Can you repeat the name of the inequality?
Grunbaum. So G-R-U-N with a umlaut, B-A-U-M. Very important inequality. So I fix a convex body. I look at the center of gravity, the center of mass. Okay, so I just integrate with respect to the Bubeck measure on this thing. And now I look at a half space that contains this. And what I'm going to say is that this half space contains a lot of the volume of K. Then the volume of K intersected with H is at least 1 over E times the volume of K. Okay, so the picture is like this. This is my convex set K. Okay, my center of gravity is maybe somewhere here. And I have a half space, maybe that one. Okay, so this is my half space which contains this point. So this point is the CG of K. And what I'm saying is that this intersection contains a constant fraction of the volume of the entire set. Okay. Of course, here I took the one that looks bigger, but you know, what I'm saying is that if this is CG, then also say, for instance, this contains a constant fraction. Okay. So any half space that contains this point contains a constant fraction. And in high dimension, if this is like a simplex, like most of the mass gets to the base like this. Okay, so this point in high dimension is going to move over there. But anyway, this doesn't really matter. Okay, so this is the inequality, which we're not going to prove. It's not that difficult, but that's not the point of the class. So let's see how to use this. Okay, how are we going to get half spaces by making gradient queries? Well, when I make a gradient query, what happens? I know that f of xt, say f of x is lower bounded by f of xt plus grad f of xt in a product with x minus xt. Right? That's the fact that that's convexity. It's just the fact that I have a lower bound, a linear lower bound on my function. So this is bigger than f of xt for any x in the half space ht, which is defined by all the x such that grad f of xt in a product with x minus xt is non-negative. Right? I query this point, I get a gradient. Anything which is positively correlated with the gradient, on that direction with respect to the gradient, the function value must increase. Or it must be non-decreasing at least. So I know an entire half space which is worse than my current point. So let me just remove all of those points. Okay, so center of gravity algorithm. So the center of gravity algorithm is like this. Let k0 be k. And for any t bigger or equal than 0, do the following. xt, take it to be the center of gravity of your current set. And kt plus 1, just take it to be kt, where you have removed this half space. So intersected with kt minus ht. I guess, what am I saying? I just want this. This is just kt minus ht. Okay, I just remove this half space. right? So imagine this is my current set. I believe, like I know right now that the optimum must lie in this set. And I query the center of gravity. I get a gradient. Now I know all of those points, they have value at least bigger than me. Okay, so I'm at least as good as everybody here. So let me just remove all of them and now shrink. Okay, so now I use this smaller set. What does Grunbaum's inequality tell me? Tells me that I have discarded the constant fraction of the volume. Okay, so let's call this G, inequality Grunbaum. Then what G tells us that the volume of KT is smaller than 1 minus 1 over E times the volume of KT minus 1. Okay, so by induction, I get that this is smaller than 1 minus 1 over E to the T times the volume of K. So I shrink exponentially, right? My volume is going down exponentially. Yes?
So, is Grunbaum's inequality sharp?
Yes.
That's very surprising, I think. isn't
What?
it?
Why?
Because I would expect, so 1 over E is less than a half. So I would expect that the side of the half of the convex body that contains the centroid to have at least half the mass.
No, so this is, okay. This is for any half space. So it's true for that guy, but also the flip. So, I'm saying, so say Grunbaum is true with constant C. This has to contain fraction C, and this one has to contain fraction C. For any H. So, yeah. I mean, it is indeed surprising, but it's surprising that you get some constant. I mean, that there is something. Yeah. Okay, so let me end this. So yeah.
H is a half space though, so it's half it's not any set. It's any set that
That's right.
bisects the space.
Yes. It's a half space, yes. I mean, yeah. It's kind of the strongest statement you can imagine because another way to put it is that the volume is smaller than 1 minus 1 over E. And if you say volume is smaller, then you can say, instead of any half space, you can say any convex set that contains the CG. But kind of the worst convex set I mean, the biggest convex sets are half spaces. So this is like, yeah, there are many small reformulation of this that, make certain surprising aspects of the inequality more apparent. Here I just took this one because it's nicer, but yeah.
If, let's say, K0 or K is just some simple polytope.
Yes.
Then at each step T, you have a slightly more complex polytope.
Sure.
So the computation to compute its center of gravity goes up.
Of course.
So aren't you screwed again?
Yeah, definitely. But that's, yes. So we're good. Yes, absolutely. But note that I'm not really so far talking about computational complexity. For instance, what I said at the beginning was that I was going to assume that my set K is simple enough.
But the point is the KT become progressively more complicated.
Absolutely. No, totally. So this is not really an algorithm per se, certainly not in high dimension. This is more like an idea on which you can build efficient algorithms. So how are you going to build efficient algorithm? You're going to go back to this, and you're going to try to prove a similar statement for another type of centroid, which is more efficiently computable. And there is a long line of work still ongoing, and the world expert is here, Yentat Lee, there are still many, many beautiful things to be discovered. We don't really understand like what is the final answer to that question? Like how to make the best computationally efficient version of Grunbaum's inequality. But for instance, the ellipsoid algorithm is exactly one way to make this efficient, but then it's not as good in other respects. But I don't want to go in that direction. It's like a different line of convex optimization. Okay, and any other question before I prove the statement? Okay, so the theorem is like this. After of order of n log 1 over epsilon steps, f of xt minus f of x star is upper bounded by epsilon. Okay, very, very nice statement. Yeah, so in fact not even. So say f is bounded. F goes from k to, I guess I want minus 1, 1. Okay, just say you have a bounded function, not even necessarily Lipschitz. If you do n log 1 over epsilon steps, you're good. So this is much better than what we were proving with gradient descent, right? Gradient descent is 1 over epsilon squared, right? A 1 over square root t guarantee in terms of epsilon that translates into a 1 over epsilon squared. Okay, so you're much, much faster. Like another way to say this is f of xt minus f of x star is upper bounded by exponential minus some constant times t over n. Okay, so you're exponentially decreasing instead of decreasing as 1 over root t. So we really beat the lower bound over here. Okay, and this is optimal. This you cannot do better even in low dimension. Okay, so let's prove this. Sorry. So after that many steps, what do I know? I know that the volume, after some constant, if I do n log 1 over epsilon step with some constant, then the volume is going to be as small as epsilon to the n times the volume of k. So after that many steps, the volume of kt is smaller than epsilon to the n times the volume of k. Okay, so you get some tiny region. Note, when the volume is small, it does not necessarily mean it's actually tiny, right? It could be like a small pancake, but it doesn't matter for what we're going to say. So next, what I'm going to say is that there is a region of good points which has volume bigger than this. So if there is a region of good points that has volume bigger than this, it must mean that I have cut one of those points before. So I am better than one of those points. Okay, so the claim is there exists a region omega such that for any x in omega, f of x minus f of x star is smaller than epsilon. Yes. Thank you. There is a region omega subset of k such that for any x in omega, x is good, and the volume of omega is at least, maybe let me put a strict here, is at least epsilon n times the volume of k. And I claim that if this claim is true, then that concludes the proof. Why again? I end up with a set, like, I must have cut a point from omega. Okay, so this inequality, this implies that omega is not included in k, t. Right? Because if omega was included in kt, the volume of kt would be bigger than the volume of omega, which is bigger than epsilon n times the volume of k. So this implies that f of xt minus f is smaller than f of x for some x in omega. But all the points in omega are good, so xt is good. Okay, that's the reasoning.
You really have to show it for all of the x in kt, not just for some x in kt, or?
I actually prove it for literally xt. Yes, you're right. Not for all x in kt. So, yeah, so I'm also using the fact that xt is better than all the points that were cut. Yeah, any point that was cut, any point which is outside of kt must have function value worse than xt. Yeah, I'm using that. Okay, and the region is very simple. You just define it by convexity. So proof of the claim is just take omega, which is a set of points 1 minus epsilon times x star plus epsilon x. X is in K.
So now you can query the function because to find out x star.
No. I'm not querying the function. Why would I need to query the function? This is like an abstract analysis. This does not go into the algorithm. Yeah. Okay, I just defined this set omega. So it verifies everything. Like by convexity, f at a point like this, it's smaller maybe with a 2 epsilon, doesn't matter. It's smaller than 2 epsilon. It's just smaller than 2 epsilon because f is bounded. Okay, 2 epsilon plus f of x star. What else? What else do we need? The volume is bigger than epsilon n times volume of k. This is because I have epsilon times x. So I can just do a change of variable, and I get the epsilon n that comes out in the volume computation. Okay, that's the proof. Any question on this proof? So again, this is not really an algorithm. It's an algorithm in this oracle model where, you know, like any computational routine on K, you can do it. And the only thing that I'm monitoring is the number of gradient calculations. In that model, this is a perfectly valid algorithm. It's not something that you can run efficiently, computationally efficiently. What I'm trying to get at is that there is a difference between computational efficiency and gradient efficiency. These are two different things. But of course, we don't know how to prove lower bounds in the computational models. Okay? The fact that we can prove lower bounds here is because we are in an information theoretic setting where what is the information that's missing? The information that's missing is the one about f. We only know f up to something. Yeah.
When you say that gradient efficient, you mean queries to the oracle?
Yes. Like making as few queries to the oracle as possible.
So a similar result for when the oracle is random, the gradient oracle.
Okay, can you make...
The dimension doesn't matter, right? So it would make sense to look at low dimension.
Yeah, so we just proved that even in dimension 1, you cannot do better than 1 over square root t. Right? So really, when there is noise, yeah, low dimension, you cannot do anything. And you know, from the convex geometry perspective, it kind of makes sense. Like basically the high dimension can simulate basically the noise in low dimension. Okay, so I'm not going to have time to do this. I will do it tomorrow. But 4 is going to be beyond 1 over square root t in high dimension. Okay, so 1 over square root t, you should imagine, you should think, is a bad rate. Like, so this is a 1 over epsilon squared rate. So imagine that I want epsilon, to be 0.1. That's already 100 gradient queries. But in machine learning, what is a gradient query? A gradient query is an entire pass through your data set. So 100 queries, you're not happy. Okay? What you would like, actually 100 is typically what people do, but you don't want to reach 0.1, you want to reach 0.01. Okay? And now we're talking about 10 to the 4 passes on your data. And you've never heard anybody in machine learning talk about 10 to the 4 passes through your data set. Okay? You want to do 50 to 100 or something like that. So you really want to go beyond this 1 over epsilon squared. We would even be happy with a 1 over epsilon. That's already much better. Okay? And we're going to see exactly what are we going to see. We're going to see that curvature, which is useful in machine learning because we care about regularization. Curvature would lead to a 1 over epsilon. And then we're going to see that smoothness. If you assume smoothness, which you can, for instance, if you do logistic regression instead of SVM, then you can also get 1 over epsilon. And if you combine both, then we'll get log 1 over epsilon. Okay, so if you do regularized logistic regression, then you're very happy. You can optimize very fast. Just a couple of passes through your data set. So that will be tomorrow. And we'll also talk about acceleration and acceleration for finite sums and stuff like that. Okay, that's it for today.